Hypothalamus artificial intelligence, HI. Digital transformation powered by real-time autonomous and intelligent algorithms. Presents the conference. Case, Oil Refining and Industrial Services Integrated Optimization in PETROBRAS. This case is based on the paper Operational Optimization of the Utility System of an Oil Refinery. PETROBRAS Recap Refinery develops a mathematical programming model, applied to the operational planning of the utility plant, as well as its interconnections with the process units. The problem is formulated as a mixed integer linear programming, MILP, model where the mass and energy balances, the operational status of each unit, and the demand satisfaction, are defined in multiple time periods. The model determines the operational configuration of the plant, by minimizing utility costs, and identifies steam losses as well as inefficient units by comparing the optimal solutions with the current operation. The MILP can accurately represent the topology, and optimize the operation of the real-world system, under different utility demands and abnormal situations in single and multi-period scenarios. Continuous and binary variables are defined for the proposed model. For instance, continuous variables represent the flow rates between the units, whereas binary variables denote the operating state of the unit, on or off. These variables are defined for every period t of the horizon considered. It is assumed that the units and external sources, for example electricity concessionary, can complement internal generation, and therefore supply the sets of variable demands in each period. Description of the utility system. The figure presents the simplified flowchart of the recap central utility system, in which each unit connected to utility header UT, is represented by a rectangle that contains its identification. This configuration considers only the systems that are subject to optimization. The initials used to identify the entities of the system are J pumps and ejectors, GV or L furnaces and boilers, M heat exchangers, O or P vessels, TF valves, and V blowers and compressors. The utilities that are considered in the optimization problem are superheated steam, V30S, saturated steam, V30, and its condensate, CV30, bar steam, V5, and its condensate, CV5, and bar steam, V1, and its condensate, CV1. There are also two other headers for condensate, that are CVV and CM, which originate from the vacuum system of the process condensation turbines. The images present the indexes and are set using in the model. Therefore, units with fixed operation do not need to be modeled and their operating variables, they are simply included as parameters that are calculated from material and energy balances. For a given header of utility UT, their aggregated values are given as a summation in the term denoted UTCF. An example of the simplifications introduced to represent the headers is shown in the figure. For the case of the V30S network, each unit is represented by a rectangle that contains its identification, and it is associated to the branch that symbolizes the process area to which it belongs. The minus sign under each rectangle indicates V30S consumption, whereas plus +sing denotes its production. The figure 2b shows the modeled system. The variables used are presented in the image on the right side. They are identified by their first letter. E continuous energy flow rate, Q continuous heat received from external sources, it is only positive for the boilers, 0 for all other units, V continuous volumetric flow rate, Y binary, equal to -1 if unit operates in period T, 0, otherwise. The images present the parameters used by the model. A unit may produce and consume one or multiple utilities. If a unit produces utility UT, it is sent to its corresponding header. Similarly, if utility UT is consumed in a certain unit, it is sent from its corresponding header. The figure generalizes this idea for every header of utility UT, denoted by CLUT. In this figure, the utility stream UT that is generated in unit EQ is sent to header CL UT at time t with flow rate VEQ UT CLUT T. This header receives all the streams of utilities that are produced in the same time period from all EQ that are mixed at the temperature and pressure conditions of the header. Similarly, Header CLUT sends utility out at time period T to consumption units. A decision variable YEQT is associated with flow rate variable VEQ at ET. The image presents the main service units included in the model: boiler, vessel, pump with electrical drivers, and pump with turbine drivers. The cases presented are applied to single period operation. In other words, there is one set of utility demands to be satisfied, which is obtained from the data acquisition system, and thereon the configuration of the plant is optimized. Different single period scenarios are considered. Firstly, the model was validated to verify consistency of the formulation, basically by eliminating the degrees of freedom and providing reference values for the economic objective function as well as for the operating conditions of the optimization model. For this reason, 3 base cases were developed: Base 1, Base 2 and Base 3, that correspond to 3 different operational conditions of the plant. Cases Base 1 and Base 2 correspond to operational conditions of the plant in typical days, without abnormalities. The objective in this study is to validate the model, and to evaluate the effect of the manual planning in the operation, in particular its economic impact. Case Base 3 considers an atypical situation given by the shutdown of U570, which generates a large portion of EE as well as V30 and V30S. The table presents the comparison of the base cases with the solution of the mathematical model. 1 means that the associated unit is up and running. Table presents the flow rates of the electric energy and fuel streams that can be optimized. Table shows the base case and optimal results for the amounts of utilities that compose the objective function, as well as their prices and corresponding operating costs. The examples show that lower cost alternatives are obtained with the optimization approaches. These alternatives would not have been considered in real-world operation, based on the configurations that are usually operated in the plant. Moreover, these are practicable solutions that satisfy the plant constraints and the set of utility demands. In the Opti4 case study, the demand profile results from frequent operational abnormalities, such as the shutdown of Unit US3, loss in the electricity supply from the third-party concessionary that is responsible for 25% of the electricity demand, shutdown of the turbo expander/electric generator unit that satisfies part of the electricity demand, and the shutdown of the L572 heat recovery boiler, which reduces the availability of the steam generated by the recovery of the energy from the process. Due to unit's shutdown, it becomes necessary to relate all flow rates to, and from, the process units and headers, with binary variables, that represent their operational state. The model must account for the loss of revenues from shutting down the process units. This is done by incorporating the revenues from the process units and multiplying them with binary variables that denote their operation in each period. The optimal solution for Opti4 is presented in tables, where the flow rates and operating state of the main units are shown for the 4 periods. The figure depicts the main currents for all periods. The table presents the results of the utilities that are considered in the objective function, as well as their unit prices, and corresponding operational costs. It is important to note that in case 4, as there are many utilities involved in the multiple time periods, it is not straightforward to analyze the effect of abnormal conditions on the operation. The optimal operating costs obtained in time periods 1, 2, 3 and 4, are $3,472, $3,472, $4,334, and $4,695 per hour, respectively. The revenue loss due to the shutdown of Unit US3 was $41,846 per hour. Finally, the last case study presented consists of a problem with 12 periods. For the first time periods, the data are the same as the Opti4 case and from then on with variable utility demands. The optimal profiles of the main utilities, electricity, superheated steam, water, and fuel and natural gas are given. The next step is to energetically integrate the system, with the entire refinery, to further improve the operation of the system. More complex multi-period scenarios were studied that consider the existing flexibility in the industrial plant. These correspond to changes in the operating conditions and in the configuration of the processes, interruption of electric energy supply from the local concessionary, equipment shutdown, for example, propylene unit, turbo expander electric generator, and results in a variable utility demand along the time periods and generated an average savings of 3 to 5%. The MILP is currently integrated with the refinery database for the planning of the refinery utility system and effectively optimizes the financial performance of the thermoelectric plant with no capital investment. The PETROBRAS mathematical model can accurately represent the topology and optimize the operation of the real-world system under different utility demands and abnormal situations in single and multi-period scenarios. The model is currently integrated with the PETROBRAS plant database and used for the planning of the recap refinery utility system, achieving up to 10.7% reduction cost in static optimization for redesign the configuration of the service plant, and 3 to 5% average savings for dynamic operation of the integrated systems. All this in controlled experiments. Like Herbert Simon, hypothalamus artificial intelligence believes that the computer-based mathematical modeling is the greatest invention of all times. Thank you for your attention.